Lawrence Technological University. I'm Paul Wright. I'm the project manager here. We're going to have a quick overview, the team introduction, the previous design history, new platform, sensors, innovative features. We'll do everything about how we did our software and round it up with a summary and then go straight into the Q&A. So let's get started. Okay, we'll start with the team introduction. I'm Paul Wright, Bachelor of Science in Technology Management. I'm the team leader and the mechanical team leader. I'm also the designer of the robot and did most of the principal machining involved. And we will introduce Ryan Matthews, who's the programming engineer.
I'm Ryan Matthews. I'm Bachelor of Science in Computer Science. I was the software team leader this year, and I also worked somewhat on the electric stuff.
Jonathan Gonzalez not here, but he is our electrical design leader. My name is Jonathan Nabosny. I was working on a global grid. I'm a Bachelor of Science in Computer Science. Just kind of got cut off.
I'm Philip Migos. I was part of the mechanical team. Just worked on different mechanical pieces of the robot.
And provided the band to bring it here.
I'm Anthony Knapp, major in robotic engineering and
All right, let's move on now that you know everybody that was able to make it. Most of everybody's working. The previous design history, the Culture Shock 1 in 2001 and Culture Shock 2 were sort of the predecessors to what you see here. It's been an evolution. The motors, some of the parts that are in here have carried over all these robots because they work so well and also for cost considerations. This is the Culture Shock 2, which is the latest design iteration of this long line of famous robots. The performance. One of the big features that we wanted to have was a very low center of gravity so that it has a low energy point of staying stable, that even when going over terrain, it's going to naturally want to stay upright and keep the sensors as perfectly level as possible. You can see a lot of the other features we have in there. Camber field design was a big improvement step. Dual chain sensors to keep the encoders that are on the motor synchronized with the wheel when it goes forward and back, because there's a certain amount of backlash that goes in there, and that's reduced into like maybe a degree or two. We have a number of safety features. We're going to keep going along so we stay on track here. You can see that we had durable materials. It was mostly aluminum for lightweight and also electrical shielding. Small footprint, less than 32 inches, so it goes through an open doorway. So we run this inside in the wintertime all the time, through classrooms and everywhere. It's kind of neat. The big step was reducing the camber angle from the previous 10 degrees to 7 degrees. You can see right there that our contact pads there, we didn't get full contact, and so in some cases we noticed last year we were getting some slippage on the ground. This also allowed us to raise up the center of gravity, or raise up the ground clearance by 2 inches, and it allowed us to package better suspension travel in there, so that's all we provide. The other thing was building a sensor card for parallel path sensor development, and also a 12-volt DC monitor eliminated the AC inverter that we had to run and all that extra wiring in there. Here's the sensor card here. We made it out of wood. The laptop goes on there. We can bolt all these things at the same height and hoop, and they can run it around and calibrate sensors and things, and that was a big improvement there. Now we'll go on to the stereo vision setup, and Ryan will take that over.
For stereo vision, this year we kind of scrapped the old side we were using a dairy system stereo camera, which are roughly $1,000 we were getting before, but they weren't working as well as we could have hoped. So this year we started new. We got just off-the-shelf webcams and did our own implementation of stereo vision using OpenCV. We used the C# wrapper and actually converted all of our code from the previous year we did in Java. We scrapped it all, started anew. Because of our stereo vision, so we keep things running fast and efficiently and actually do really well with their stereo vision. We are using the stereo vision in the disparity image, which you see up at the top, than just the grayscale. But to make it easier for us to work with when we were trying to debug it, to make sure we did valid images, we have that bottom image, which is showing the actual obstacles and the colors and distance they are away. So it goes from green to red. Wherever you get, the farther it is away. The greener it is, the closer it is to us.
All right. Along with the vision, we have a global grid, which is how we run a pathline. The global grid is a buffer essentially between the camera images that we get into the global pathfinder, which is how we navigate the robot around. As you see on the left, this is just an image taken from Google Maps with some coordinates here. To get the grid, what we do is we take the northernmost latitude and the southernmost, and then the western and easternmost longitude, and we create this nice bounding box here. So those are just some sample coordinates, and then they create the actual bounding box. Then what we do is we take that and we can adjust the space size Y, and there's also a space size X, so we can adjust the resolution of our grid. If we want bigger grid spaces, smaller grid spaces, so we can do things faster, or we can have a little bit more larger objects in each thing. This is kind of just a little example. On the left, this is just an example of what we had. This is some from the actual code on the right. So on the left, you see some things like barrels or lines, and then on the right, this was just after we started the program. You can see just that little white line there is basically a line. As you see, obstacles and other things that get painted on the screen. The red lines are a little hard to see. That's actually our vision. And what we can do then is we can clear away points that we're seeing new instead of leaving this noise.
Pathfinder this year we used Data Star, which is slight variation. A Star, there's not too much to it, but it's a big improvement from how we did it last year. We planned points to all the paths, and then individually from point to point. So we're going to waypoint 1 and waypoint 2. We can do those independently of plan your paths to all of them to keep efficiency up. JAWS this year is the same as the previous couple years, so we re-implemented our Java code in C#. So we have a connector. We have our Java JAWS code, which has been the same for a few years now. We integrated that to work with our new C# code, and they talk together using a TCP connection.
All right, let's round up a little bit with some of the innovative platform features, the camera wheel design, of course, but also single-sided mounting. It's easy to replace the wheels. And everything is symmetrical side to side, so we can have one part, we only have to make the replacements will fit either side. The lower center of gravity, all the rest of the stuff, the stereo vision is proprietary to us. We also have all these features here that are the same as last year. In summary, this has been an evolutionary process over all the 4 robots. We keep seeing great leaps forward as we go, and we're having great anticipation in the future of really being able to knock this out of the ballpark, because we're getting real close to having, all these things tied together. So I believe we're ahead of time, and we can go to the Q&A. Depending on the subject matter expert, I'll direct you to whoever knows the most about it.